I know I'm recording now. All right, so we're going to take a look. Homework 2.2. Someone asked a question about the homework 2.2 question 4. So I'm going to talk about that first. All right, so here's the problem. Ugh, that's just going to land right on top of that. And then, there we go. Okay, so here is a polynomial function. Answer the questions regarding the graph of f of x. Use this information to graph the function. Choose the end behavior of the graph of f, and end behavior is controlled by leading term. What is the leading term in this? F of x is equal to x plus 2 times x minus 1 times x minus 2. The leading term is going to be x times x times x, which is going to be x cubed. All right, so that's odd. So it's either going to go like this or the opposite. Okay, what controls the end behavior? It's the sign of that leading term. Leading term is positive, so that means as I go toward positive numbers, I get more positive. As I go toward negative numbers, I get more negative. So there's my end behavior. List each real zero. Okay, and note the difference between zeros where we cross and where we don't. I can actually just bring this over and actually type it directly in so you can see. End behavior is rises. You'll see falls to the left, rises to the right. Zeros where the graph crosses the x-axis, zeros where the graph touches but does not cross. Crosses are odd powers, and touches are the even powers, the multiplicity. Each one of these has a multiplicity of 1, so they're all odd. So it means that all of these are places or zeros where it crosses. The zeros are -2, +1, and +2. I did that by just taking the factors, setting them equal to 0 and solving. It does not touch at any of those. It doesn't touch and then go back in any of those. Y-intercept, let x equal 0, solve for y. That's 2 times -1 times -2, which is 4. And I would love for that to be accepted as an ordered pair, but it won't be. So we just put 4. And then graph. Plot all the points for the graph of f of x intersects the x-axis. For each point on the x-axis, select the correct information. So put all the points down. I touch the x-axis at negative, or across at -2. And then at 1. And then at 2. Now, my end behavior is going to help me out of this one. Falls to the left, rises to the right. So let's start over here at -2. If I'm falling, right, if as x goes negative, the whole function goes negative, this is what this is supposed to look like, right? I'm going to be falling to the left and rising to the right. The next one is the last one. Go to the last one on the right, which is 2. And at 2, I got to be doing the same thing, right? I'm going to have to be rising. So that means at 1, what am I doing? Well, from -2, I've come up from negative infinity. I've crossed the x-axis. And now I've got to get back down below it so I can cross it again. So there are those 3. You need, and a y-intercept. The y-intercept was 0, 4. And then you just click on that button to graph and check your work. I have to type the word none. Sorry, didn't even read that. There's no answer. Oh, click on none. Oh, yeah, there you go. Okay, let's see if we did it. All right. I love that question. Except for the intercept problems. All right. How's that feel? Good. Good. Yeah, in behavior is going to tell you how your leftmost and rightmost x-intercept behave. And then it's kind of realizing that if I'm going to cross at -2, that means, and I'm crossing going left to right from -2, and I'm crossing at 2, then that means that root at 1, you've got to be diving from left to right. You got to be falling from left to right to get there. All right, and again, this is a sketch. The computer obviously can calculate the answer pretty quickly, and it did. Just as long as you're following that pattern, you go up high enough to catch the 4 for the y-intercept, come down, go up. They can be, I mean, these can be extreme. You could have between 1 and 2, this thing might dive down to -3 million for some functions, not this one, but right, it can go as low as it wants to, but really all I'm worried about is it crosses and it crosses. All right. What else? 2, 2 is really short. Okay. All right. Okay. So yeah, I'm going to keep this. I like that question. I'm going to keep it in the notes for later. Question 6. Come back. Preview question 6. Below is a graph of a polynomial function with real coefficients. All local extrema of the function are shown in the graph. Determine with the factor. Yeah. Okay. All the local are marked with the little x's. Okay. Over what intervals is the function increasing? So reading from left to right, I'm going up here, and remember that's between x values, not y values. So starting at -9, or starting just to the right of -9 and going all the way up to -7, then I fall, and then I stop, and then I start to rise again. That starts at -3 and goes until 1. And then I fall, and then I rise again from 4 to 6. And that's it. The reason I'm pausing is they're missing an interval here. Yeah, they didn't put the -7 to -3 is not even an option, so I don't know why. At what x values does the function have a local minima? If there's more than one value, separate them with commas. So each little x is a local max or min. These are mins that we're looking at. So I have a min at -9. I have a minimum at when x is -3, and I have a minimum when x is 4. Good. sign of the function's leading coefficient. This is an odd function because it's, remember, in behavior, when I'm dealing with an odd function, one goes to positive infinity, one goes to negative infinity, right? So this is odd. The question is it the normal odd, where as x gets larger and larger, the function gets larger and larger, and as x goes more and more negative, the function goes more and more negative, or has it been flipped? In this case, it's flipped, right? X is growing, x is getting larger, but my output is getting more and more negative. That means my leading coefficient must be negative because it's flipping that behavior. So instead of as x grows, y grows, as x grows, y falls, as x goes negative, y grows. So that means I'm looking at a negative leading coefficient, which is following is a possibility for the degree of the function. Choose all that apply. Well, there's two ways to go after that. We know it's odd, and a function, when I graph a polynomial, if it has a degree of n, then that means it can intersect the x-axis at most n times. All right, so that means I've got 1, 2, 3, 4, 5. So I cross 5 times. 1, 2, 3, 4, 5. So that means I could have a 5th degree polynomial. I can't have a 6th degree because of the end behavior. I could have 7th degree, and I could have a 9th degree, just based on the intersections, okay? All right, so and then how many turning points do I have? How many times do I change from increasing to decreasing? 1, 2, 3, 4, 5, 6. Okay. So I can have, a function can have at most n x-intercepts or n minus 1 turning points. All right. So this function changes direction 6 times. So that means this must be a 7th degree polynomial or more. So I'm going to do 7 and 9. I'm interested. Yeah. So 7 or 9. Okay. So really what you're after there is the rule with the turning points. That's probably the whole purpose. That I know that's the whole purpose of question 6, is to really tackle that. If I have so for instance, if I have let's jump back to this extra page here. Okay, if I have a parabola, right? This is plus 2x plus 1, something like that. Okay, 2 zeros, 2 x-intercepts, or 1 turning point. Right? I changed my behavior from decreasing to increasing. So at most, n real zeros, or n, sorry, and n minus 1 turning points. Okay, and this this is at most. It doesn't mean it has to happen, at least for the turning point, for the real zeros, but the turning points are helpful. So if I go down, up, okay. If I just look at the zeros now, it looks like I have 2 of them. But this can't be a 2nd degree polynomial because how many times did I change directions? I changed directions here, I changed directions here, and I changed directions here. So that means I got 3 turning points, which means I must have at least a 4th degree polynomial. All right, so yeah, focus on the turning points for those questions. 3 turning points. Degree in is at least 4. All right. So there's number 6. All right. Keep working on it. I know everybody's doing what they can, and by all means, questions are great. So last class, I know we did this long division, and then I introduced you to the equation. This one was long division, and it's the first example, but it's got that the divisor has the x squared. You're not typically going to see that. You're typically going to see something more like example 2 or example 3. I have done examples 1, 2, and 3 already. But let's make sure. So let's go after example 2. I may be repeating myself, but that is completely fine. I'm dividing. Remember that this, because this comes up later, this same problem can be written like this, and it means the same thing. All right. The reason that you would want to write it like this, perhaps, is because if you don't put parentheses around the entire numerator and the entire denominator with the divide symbol, you'll get it wrong. So that's another way to write it. Notice I'm missing a term. I don't have an x term here. So I have x cubed, x squared. I don't have an x term, so I am plugging in a 0 for that. And I'm going to go ahead and start feeding you some work here. Divisors x minus 5. Dividend 2x cubed minus 7x squared plus 0x minus 65. And so as I do this problem, leading term of the divisor goes into the leading term of the dividend how many times? Or in other words, you can see it 2 ways. You either see it as 2x cubed divided by x equals what? Or what do I have to multiply x by to get 2x cubed? In both cases, the answer is 2x squared. 2x squared is the first term in your quotient, and then you multiply just like regular long division. 2x squared times x is 2x cubed. 2x squared times negative 5 is negative 10x squared. Remember, this is subtraction. 2x cubed minus 2x cubed, we knew that was going to go away. Negative 7x squared plus 10x squared is negative 3x squared. I only have one term now. Great. Bring down the 0x. X goes into negative 3x squared, negative 3x times, or I need to multiply x by negative 3x to get negative 3x squared. Is everybody okay with that? Does that make sense? Let me get the color stuff working here. Not negative, positive. All right, 7 minus negative is plus, so this is 3x squared. Bring down the 0x. I knew there's a reason I wanted to rewrite that. Let's try it again. So now, the rinse and repeat part, my new leading term, 3x squared. I divide it by the leading term of the divisor. 3x squared divided by x gives me 3x. Or what times x gives me 3x squared? 3x does. 3x times x, 3x squared, 3x times negative 5, negative 15x, subtract 3x squared minus 3x squared is 0. 0 minus negative 15x becomes positive 15x. And then last term, minus 65. And last time, leading term is 15x. Divide that by x. And the result is 15. 15 times x is 15x. 15 times negative 5 is negative 75. Subtract 15x minus 15x is 0. Negative 65 minus negative 75. Minus negative becomes plus. So this comes out to a 10. All right. Now, what's the last? How do I put all of this together? So remember, when I get done, what I'm going to be able to do is rewrite that division as multiplication, just like we did if 81 divided by 3 is 27, then 27 times 3 is 81. Same thing here. P of x is the original, and the original is that 2x cubed minus 7x squared minus 65, yeah, is equal to the divisor, which is x minus 5, times the quotient, which was 2x squared plus 3x, plus 15. And then plus the remainder. All right, so that's long division. If I did this one last class, you may have caught me making a mistake here and making this 65 and 65 so that zeroes out. It's not. On the first set, the first video, I make that mistake on the for lecture for 2-3, but then I fix it first thing in the second part of the video, so it should be flawless. So we got another one, and then let's get synthetic division worked out. Okay. So with synthetic division, we did one of these last time. If I am dividing a polynomial by a binomial that has a leading coefficient of 1 and a power of 1, so it's pretty much got to be x, or whatever the variable is, plus or minus some number, I get to use synthetic division. All right, synthetic division it does long division, but it does it efficiently. So the first thing I have to do is figure out, if I'm dividing by x minus 2, what is the x value that I'm checking for? Well, it's whatever makes this 0. What makes x minus 2 0? 2. So 2 goes in the box, and then the coefficients from the numerator come along for the ride. 2, 13, negative 3. I don't think I'm missing any. Negative 58, negative 20, and 24. Okay. All right, so now synthetic division, step 1. Bring down whatever that first coefficient is, because that's going to be the coefficient that begins the quotient. All right, so bring the 2 down, and then we play the game. And we take whatever's in the box here, multiply it. 2 times 2 is 4. And then we add 13 plus 4, 17. 17 times 2, 34, which is obviously why I wrote 38. Sorry. Let me get this page right back here. Yeah, that's obviously what I meant. 17 times 2, 34. Negative 3 plus 34, 31. 31 times 2, 62. Negative 58 plus 62 is 4. 4 times 2 is 8. Negative 20 plus 8 is negative 12. Negative 12 times 2 is negative 24. 24 plus negative 24 is 0. So that means 2x to the 5th plus 13x to the 4th minus 3x cubed minus 58x squared minus 20x plus 24 is equal to the divisor, x minus 2, times the quotient. Now, what's the quotient? The quotient is, I started out with a 5th degree polynomial. I divided it by a 1st degree polynomial. So that means the highest power in my quotient is an x to the 4th. So that starts out 2x to the 4th. And then you're just reading down the line. Plus 17x cubed plus 31x squared plus 4x minus 12. And then the remainder plus 0. You don't have to write that, but you can. All right. So I want you to take a look. Since that remainder is 0, I actually have a direct relationship between the polynomial I started with and the quotient and the divisor. So I've actually found out that if I get a remainder of 0, x minus 2 actually goes into my polynomial, meaning I'm going to end up with a set, or I'm going to end up with 2 factors of the original polynomial. And that is going to be helpful for us because all we've done up to this point is a few cubes, special cubes, and then we really focus the rest of our time on solving quadratics, solving 2nd degree polynomials. All right, so that said, and this is what happens when it doesn't, right? When I did 2x cubed, this one was out of order. 2x cubed minus 10x squared minus 5 divided by x plus 1. and I did that out, I ended up with a remainder that is not 0. So that means this does not go into it evenly. So I cannot write 2x cubed minus 10x squared minus 5 in terms in a set of two factors. That minus 17 throws everything off. So we like it when the remainder is 0 because it means we did something. It means that we actually found a factor. Now, this next page is evaluate the polynomial. The only reason we're doing it is because of a property that's going to show up. This is the last problem we just did. And so here's P of X, and I want to know what is P of X when X is -1. I do not bother rewriting the order here. You can if you want to, but it is not necessary. Powers first, so -10, 1 squared, -1 squared is 1, plus 2, -1 cubed is -1, -10 times 1 is -10, 2 times -1 is -2, minus 5 more. -10 minus 2 minus 5 more is -17. So there's my point, or there's the result. P at -1 is equal to -17. All right. Now, take a look back, because I've dealt with this polynomial before. It's right there. -10x squared plus 2x cubed minus 5. And what did I divide by? X plus 1, meaning what goes in the box for my synthetic division? -1. And when I do the synthetic division, look at what pops out. The remainder is -17. Well, on this page, I just showed that the evaluation of P at that number that's in the box for synthetic division is also -17. Turns out that happens every time. So what we have is the remainder theorem. The remainder theorem says that if a polynomial is divided by x minus c evenly, all right, if you divide it, or excuse me, when you divide a polynomial by x minus c, the remainder that's going to pop out happens to be whatever you would get if you took that original number and plug it in to f of x, or g of x in this case. So again, talk. How about we do instead? Evaluate g at 2. Here's g of x. What is g at 2? G at 2 is -3 times 2 to the 5th plus 2 times 2 to the 4th plus 6 times 2 squared minus 2 plus 4. Powers first because of order operations. 2 to the 5th is 32. 2 to the 4th is 16. 2 squared is 4. Multiply -3 times 32 is -96. Two times 16 is 32. 6 times 4, 24 minus 2 plus 4. I get -38. All right. Now, the remainder theorem says if this is true, if g at 2 is -38, if I perform synthetic division by x minus c, I should also get a remainder of -38. So in this one, what we're saying, if g at 2 equals 38, comma, then g of x divided by x minus 2 will have remainder of negative 38. So let's do it. 2 goes in the box. Coefficients of g of x are negative 3, 2, 5th degree, 4th degree, missing a 3rd degree. So you need a 0 for that placeholder. 6, negative 1, and 4. Bring down the first term, and then let the games begin. I'll stop changing colors of pen, because it's just kind of silly. Bring down the negative 3. 2 times negative 3 is negative 6. 2 plus negative 6, negative 4. 2 times negative 4, negative 8. 0 plus negative 8 is negative 8. Negative 8 times 2, negative 16. 6 plus negative 16, negative 10. 2 times negative 10, negative 20. 20, negative 1 plus 20, negative 21. Negative 21 times 2, negative 42. 4 plus negative 42, negative 38. That's exactly what we said would happen. And this theorem works both ways. You'll see that it's got 2 lines. If the remainder from synthetic division is 38, then evaluating the function at 2 gives you 38. If you evaluate the function at 2 with a binomial, then you can perform synthetic division and you'll find a remainder of 38. All right, so that's the remainder theorem. All right. And again, anything you see me skipping in here that's already done, that's on the video. And do you want to see another one of these? Do you want to see this one before we move on, or does this seem fairly straightforward? Do we need to see another example there? Okay. The next part, all it does is just use the remainder theorem to evaluate the remainder when f of x is divided by each factor. So f of x is this function, this polynomial here, dividing by x plus 1, divided by x minus 3, divided by x minus 4, divided by x minus 5 halves. And what that does is correspond to, well, x plus 1 is what I'm dividing by. So I'm just checking out when x is negative 1. X minus 3 corresponds to when x is 3. X minus 4 when x is 4. X minus 5 halves means I've got 5 halves in the box. All right. Now, here's the, I probably already closed it. Yeah, I was going to say. So it turns out that we have one more piece of information. All right. So we know that I can always find the remainder. And then every once in a while, I will find a remainder of 0, which means x minus 3 goes into the original function evenly. So we officially state that as the factor theorem. The factor theorem says that if f of x is a polynomial and f at c is 0, then x minus c is a factor of f of x. And the other direction works as well. If you know x minus c is a factor of f of x, then you know that taking that c and plugging it in to f of x is going to give you a 0. All right. So let's go after this next example, and then I'll show you exactly what this does or how it translates to our graph. So here's f of x. Determine if the given polynomials are factors of it. Okay. So x minus 6 is my factor. What value, or what is c here? Remember the form here is x minus c. All right. So in this one, c is 6. Is everybody cool with that? 6 is what makes x minus 6 go to 0. So c goes in the box. Coefficients of the dividend pop in 2, negative 13, 10, negative 25, and 6. Bring down the 2. 2 times 6, 12, negative 13 plus 12, negative 1. Negative 1 times 6, negative 6. 10 plus negative 6 is 4. 4 times 6 is 24. Negative 25 plus 24 is negative 1. 6 times negative 1 is negative 6. 6 plus negative 6 is 0. So, what does that mean? All right. Well, because of the remainder theorem, we now know that f at 6 equals 0. And if f of 6 is 0, then x minus 6 is a factor of f of x. Okay? Now, I'm going to take what we just did and then write, remember the original in this one, I'm going to break it down. So now I know that f of x, 2x to the fourth minus 13x cubed plus 10x squared minus 25x plus 6 is equal to the divisor, x minus 6, times the quotient. And in blue down here below the line, those are the coefficients of the quotient. This was a 4th degree polynomial, meaning the quotient is a 3rd degree. 2x cubed minus x squared plus 4x minus 1. All right. Questions? I'm quickly running up the graph here because I want to show you what this means for the graph. All right. So in this problem, we did synthetic division. We found out that I get a remainder of 0. That remainder of 0 lets me know that if I plug 6 in for x, I get 0 out. And that means it divides evenly. What else does this mean? Well, I said when I plug in 6, f at 6 is 0, right? F at 6 is 0. That is an x-intercept. All right? That's why this is a useful piece of information. Because if I have a higher order polynomial like this, and I don't know how to solve it, what I would do, and the way that I was taught and trained, is I would graph it. I'd go find some nice solutions on that, and then use synthetic division to break down that higher order polynomial or higher degree polynomial into, as I can get it all the way down to quadratics, and then we have 5 different ways of solving quadratics. All right, that's the idea here. That's what we're after. is I'm looking for a way to solve polynomials that I wouldn't be able to solve before. That's why synthetic division and long division are really helpful, because it's the only way to figure out how do I get from x to the fourth, x to the fifth, down to x squared, unless it's substitution, which isn't the case in this chapter. Okay. Now, what if I go the other, what if I just tell you one of the zeros of a polynomial, and then I ask you to solve or ask you to find the others? So f of x is 3x cubed plus 25x squared plus 42x minus 40. And I'm given that negative 5 is a 0 of f of x. If negative 5 is a 0, that means if I put negative 5 in the box and I do synthetic division, my remainder should be 0. So let's make sure it is. 3x cubed, 25x squared, 42x, negative 40. Bring down the 3, and then start the process. Negative 5 times 3 is negative 15. 25 plus negative 15, 10. 10 times negative 5 is negative 50. 42 plus negative 50, negative 8. Negative 5 times negative 8, positive 40. Negative 40 plus 40 is 0. So that's exactly what we thought would happen, right? Negative 40 plus 40 is 0. I knew this was going to be a remainder of 0. But what does that do for us now? Well, now f of x can be written as the divisor, and instead of writing all of f of x, that's why I just put f of x as that. That's the same thing as saying x minus c. I plugged negative 5 in and got out a 0. So negative 5 is c times the quotient. And the quotient is, this was a cubic third degree polynomial. This has got to start out 1 degree less. So 3x squared plus 10x minus 8. Make it nice here. X minus negative 5 is x plus 5. And then 3x squared plus 10x minus 8. Will that factor more? No, I got a quadratic here. I bet it will. Three x squared plus 10x plus 8. I'm going to do bottoms up. Which means take a and c, multiply them together. X squared plus 10x minus 24. Does that factor? Yeah. X and x, multiply to negative 24, add to positive 10. One's positive, one's negative. And then which one's positive? It's the larger of the two. Two numbers multiply to 24. It's either going to be 6 and 4 or 12 and 2. And in this case, it's 12 and 2. Remember, though, bottoms up says, great, I'm glad you found the answer, but now come back and divide by that a, because that a and c were multiplied to give you that 24. So now come back and undo that multiplication, and you'll find x plus 4 times x minus 2/3. Now, I'm fine with you leaving x minus 2/3 as x minus 2/3 because it's useful. If you want to rewrite it as 3x minus 2, you can, but just know that the next question is going to say, it's going to ask you to solve, and you're going to end up finding that 2/3 again. So here's f of x, and it's written as a product of binomials. So then they say, now solve 3x cubed plus 25x squared minus 42x minus 40 equals 0. Well, I know that entire function can be written as x plus 5 times x plus 4 times x minus 2/3. So all I did is swap out that cubic for it, the same function or the same polynomial, but it's written in as a product, as products. Why is that useful? Because now I've got stuff multiplying to give me 0. So if stuff multiplies to give me 0, one of those things has to be 0. So x plus 5 is 0, x plus 4 is 0, x minus 2/3 is 0, and solve. And my solutions are -5, -4, and 2/3. All right. Any questions? No? Just silence? That's understandable. All right. Then let's go ahead. Yeah, it is. It is. It is a lot of work. All right. So let's tackle this last problem out of 2-3. And I've got it titled as complex zeros. Everything we've done up to this point has been, I give you the function or I give you the polynomial, and then you break it down into its component parts. This time I'm going to give you the component parts. I'm going to give you all the zeros, all the values of x that make this function 0. And I'm going to ask you to find the function. All right. So I'm told that I have 3 zeros, 8, 2 plus 5i, and 2 minus 5i. So I put those zeros down. And now I want to really drive home this idea that if 8 is a 0, then x minus 8 is a factor, right? The factor is always x minus c. If you tell me a 0, I can tell you a factor of the polynomial. Now, this is a complex 0, so it's x minus c. And this, remember, c is the entire number, 2 plus 5i. Don't forget those parentheses on the inside, or it will not distribute correctly. Same thing down here, x minus 2 minus 5i. Turns out if you have complex zeros or irrational zeros, that the conjugates will always be zeros. So conjugate just means these two terms are added and now they're subtracted. That's the difference in them. These two numbers are called conjugates of each other. Everything's the same except for the operation between them. Okay, 2 plus 5i, 2 minus 5i. 7 plus I, 7 minus I. Those are called conjugates. And they always pair up. If you know one of the conjugates is 0, the other one automatically has to be. But let's continue the math. X minus all of that means I'm looking at x minus 2 minus 5i. And then I have x minus 2 plus 5i. Okay? So that means the polynomial that has these 3 zeros looks like x minus 8, x minus 2 minus 5i, x minus 2 plus 5i. Okay. Now, I'm going to make a slight change. I'm going to use the fact that multiplication is commutative to just swap the order here. I'm going to put x minus 8 way over there on the right because I don't want to do that multiplication first. And the reason is, if I have conjugates, when I multiply them together, I'll end up getting rid of all the imaginary factors. All the i's will be gone, and that is going to be really helpful. So I want to do that first. So I'm just going to go old school. We're going to multiply these two trinomials. We're going to end up with 9 terms from this multiplication. All right, so it's going to be x times x is x squared. X times negative 2, negative 2x. X times 5i, 5xi. And then I go down to the next term, negative 2. Negative 2 times x, negative 2x. Negative 2 times negative 2 is 4. Negative 2 times 5i is negative 10i. And then lastly, negative 5i times x, negative 5xi. Negative 5i times negative 2 is positive 10i. And then negative 5i times positive 5i is negative 25i squared. And then don't forget the x minus 8 on the end. All right, now let's combine like terms. No other x squared terms in here. 2x and 2x, negative 2x and negative 2x are going to come together. Let's see if anything goes away first. Plus 5xi minus 5xi. Those zero out. The 4 does not. Negative 10i, positive 10i. Zero out. And then look right here. I squared is negative 1. So the reason that I multiplied the conjugates together is because if I did it, all of the i's would go away. Is that what happened? Yep. X squared, negative 2x minus 2 more, minus 4x. 5xi goes away, 10 and negative 10i goes away, that goes away, that goes away. And then I'm just left with negative 4x plus 4 minus 25 times negative 1. What's going to happen when I multiply 25 times negative 1? I'm going to get plus 25. So minus 4x, and then 4 plus 25, 29. All right, now let's finish it. Same process, distribute x squared times x, x cubed, x squared times negative 8, negative 8x squared. Negative 4x times x, negative 4x squared, negative 4x times negative 8, positive 32x. 29 times x, 29x, and 29 times negative 8, 70, yeah, negative 232. All right, combine like terms, wherever they may be. There you are. X cubed, negative 8x squared minus 4 more, it's negative 12x squared. 32x plus 29x, 61x, and then minus 232 is just minus 232. So this is the polynomial that has zeros of 8, 2 plus 5i, and 2 minus 5i. All right. That's 2, 3. Questions? Nothing? No? All right. All right. So 2, 3 is available. You can start looking at it. Yeah, that last page is just, it's old math, the stuff you've already done or should already know. This is the only new part. Yeah. This is the new part. If I give you the 0, you tell me the factor. But once we get to here, that's prerequisite knowledge, right? Multiplying those out is something you should already know how to do. So the only new part of that last problem, if this is a 0, this is a factor. That's the only new thing in this section. So don't let it overwhelm you. Don't think that there's so much more material in here, you're having to do so much work. No, it's old math. It's just a lot of old math. All right. So 2.5. So 2.5 is all about rational functions. Rational functions are functions that have a polynomial in the numerator and the denominator, and the denominator is not the 0 polynomial. Okay. We've seen this already. We dealt with this in the algebra of functions chapter, where we would find when we were doing add, subtract, multiply, divide, and we had a special process we had to follow to make sure that we found the correct to find the correct domain. We had to make sure that the denominator was not 0. Rational functions do have some unexpected turns and twists. These even have holes in them. So if you see this graph and you're thinking, hey, that looks a little funny, yeah, these are going to look a little bit funny. Notice that as my function looks like as I'm approaching some value of x, my function is shooting off to positive infinity, and then as I try to go after that same value from the right, it's diving off to negative infinity. Whenever that happens, what you're looking at is a vertical asymptote. Vertical asymptote is just a line, a dotted line, just a vertical line that your function does not cross. Okay? So let's see if we can put together some information on these functions. Not going to look at the graph yet. I just want to see, how do we feel about these problems? So the first one there, you got a function, and then first thing asked is the domain. So yeah, and this one's that second and third row are repeated. Oh, that's funny. All right, so f of x is 1 over x minus 4. So what is the domain of f of x? All right, well, domain, 2 questions. Do I have a variable in the denominator? Yes. Do I have a variable under an even root? No. Variable under in the denominator means I need to figure out what value of x makes the denominator 0, and that is not allowed to be in my domain. What makes the denominator 0 here? 4 does. So the domain is everything but 4, negative infinity, up to 4, 4 to positive infinity. Now, vertical asymptote. Vertical asymptotes are what happen when the denominator equals 0 and the numerator does not contain a matching factor. So what is the vertical asymptote? Take the denominator, set it equal to 0, and solve. So that vertical asymptote is x equals 4. Okay. The horizontal asymptote kind of has a three-part. It has three different possible outcomes. If so, n lowercase n is the degree of the numerator. All right. Lowercase d is the degree of the denominator. Okay. So in this first problem, the numerator has a degree of 0. The highest power of x you see, there isn't one. So that's degree 0. The denominator, the highest degree of x is 1, right? So whenever the denominator, when n is less than d, I get a horizontal asymptote at y equals 0. Okay. Why does that happen? Because, remember we talked about end behavior. As x goes off to infinity, what's happening to this with this fraction? As x gets larger and larger and larger, the denominator is growing. The numerator is standing still. So what happens to a fraction as the denominator gets larger, more and more and more? It gets closer and closer to 0. So anytime that happens, the horizontal asymptote is y equals 0. The next one, I've got 3x squared plus 1 as my denominator. Do I have any domain issues there? Let's find out. 3x squared plus 1. So jot down here, 3x squared plus 1. Remember, variable in the denominator. Take the denominator, set it equal to 0, solve. Divide by 3. X squared is negative 1/3. You already know what's about to happen, but let's solve it anyway. X is equal to the positive and negative square root of negative 1/3. And then negative 1/3 means what? I'm imaginary. Okay. The domain for rational functions does not contain any complex numbers. So the domain of rational functions does not include complex numbers. So this, so ignore these. If you want to follow the algebra steps correctly each time by setting it equal to 0 and solving, great. But then when you get here and you say, okay, well that is what causes the denominator to be 0, make sure you know that just because that is the answer here, it doesn't mean you have to remove it. That's not part of the domain anyway. So if you do your domain steps and you find that zeros are all complex, domain is all real numbers. All right. Vertical asymptote. What made the denominator 0? Nothing. So this has none. All right. And then same as before. Numerator has degree 1, denominator has degree 2. What happens if n is less than d? My horizontal asymptote is y equals 0. All right. So we're end of 2.5. Like I said, the goal is to have this done. If there's any other questions, shoot them my way. If not, enjoy the day, enjoy the weekend, have fun staying inside out of the rain.